All right, everyone, in this video we're going to look at the fundamental theorem of calculus part 2. There are two parts. We've been looking at part 1 for the last couple days, and the purpose of this video is to tell you what part 2 says and explain it to you, and then we will practice with this in class. So to understand part 2 of the fundamental theorem of calculus, let's start by taking a look at this picture. I want you to notice right away that the function I am defining is going to be in terms of t, and the reason that I'm going to use f of t is so that x can be a specific value of x along the x-axis that is a variable. It can change, and then the area underneath my function I'm going to define in terms of x, so I'm calling it a of x. So what I can say is that a of x, the area, is the antiderivative underneath the curve from a all the way up to x of my function f of t dt. This is the setup. And I really want to emphasize that this upper limit here is a variable. When we use a and b are constants. They are numbers that we can actually plug in and evaluate, like 2 and 10. But x in this instance is a variable. So if I actually anti-differentiated f of t between a and x, my area function would be defined in terms of an x. So what I mean by that is, if I gave you this question, find the area underneath t squared from 0 to x. First of all, notice that I've got a dt because my function's determined, or it's defined in terms of t. So if I anti-differentiate this thing, and then I plug in my limits from 0 to x, my answer is going to be 1/3 times x cubed minus 1/3 times 0 cubed, and this all is equal to 0. So my area is defined in terms of x, which is a variable. It can change. So depending on what x is, this new function would give me my area. So I'm defining my area in terms of a function described by x. So let me go ahead and tell you the result of the fundamental theorem of calculus part 2, and then we'll try to work backwards and unpack it a little bit. So here's what it says. All of this setup that I've established is sort of like our if clause of part 2. So if this is the case, if my area is defined as the integral from a to x, and if I am interested in finding a prime of x, or in other words, if I'm interested in finding the derivative of the integral, we already have some intuitive understanding that the derivative and the integral sort of undo each other. They are antiderivatives, but the result of this second fundamental theorem of calculus really drives that home. So here's what this is equal to. We'll cut right to it. A prime of x, or in other words, the derivative of my integral, is going to equal f of x. So it's the f function defined in terms of x. This is the result. This is my if clause. This is my then clause for my fundamental theorem of calculus part 2. So let's just see if we can go ahead and make some sense out of this using our calculus skills that we have, and actually using our first part of the fundamental theorem of calculus. If I were to take the antiderivative of, if I were to just try to rewrite this thing by using the first part of the fundamental theorem of calculus, the antiderivative of f of t is big F of t, and I'm trying to evaluate this thing in between a and x. So I'm going to end up here with big F of x minus big F of a. This is the same as this. These are equal. So the fundamental theorem part 2 is interested in finding the derivative of this function that I've called a. So if I want to take the derivative of this, I'm trying to differentiate this function. And the derivative of big F of x minus big F of a would be f prime of x minus f prime of a. And if we really think about what this is, think about the fact that big F of a is a constant. that is going to be some constant because I'm plugging a in, which is a constant, into my function, and thus generating a constant. So the derivative of that constant has to be 0 because the derivative of any constant is 0. So I'm left with this big F prime of x. And really, we already know what this is saying. This is saying find the derivative of the antiderivative. And the derivative of the antiderivative is going to bring us back to our original function f of x. So this is kind of a proof or an explanation of what this thing is saying and why this thing is saying what it's saying. Really, the big picture is that the second part of the fundamental theorem of calculus allows you to take the derivative of an integral and get back to some original function. So we'll practice this more tomorrow. I'll leave you off there.